Does your slideshow work?
Yeah.
Okay, great. I'd say we could wait, but, well, we have,
Yeah, no worries.
we do have a stack of them. What's the last time you heard from?
Yes.
So I want to half close that door. I think it's still locked, so don't, otherwise we'll get interrupted. Thank you. Thanks. That's good. That's good. Okay, Sophia, do you want to go ahead and start? Normally, I like to have your advisor introduce you because obviously they've worked,
Yeah.
closely with you over the past term.
Well, I can introduce myself. I'm Sofia Abrego, and I've been working in Fitz Lab for about 2 years now-ish. Started my sophomore summer. I've mainly been working in the machine shop, but I've learned a lot from everyone in the lab, all the grad students, all undergrads, and the Thesis as well. Yeah, thank you so much for coming. I'll be presenting my honors thesis on our work towards our optical fiber integration for surface TLS solution. So I'm going to walk us through 6 sections, starting with why any of this matters, and then I'll talk about what 2-level system defects are and why they matter to us. And I'll talk about the broadband spectroscopy platform that our lab developed, as well as some of the work I did last summer. And then finally, I'll talk about one of our current experiments with optical integration. So, starting with the motivation, in quantum computing, we have qubits, which is a quantum bit, which exists as a superposition of 0 and 1 simultaneously. Now, in order for qubits to properly work, they have to be almost perfectly isolated from their environment, while being coupled enough for us to read out and control. Now, these requirements contradict each other a bit. And on top of that, there's these tiny microscopic surface defects that absorb energy and have the qubits almost forget their quantum information. And you can kind of think about it like this, in simple terms. You're in a room, you're trying to have a quiet conversation, and there's a bunch of tiny speakers around you making random noises. That's kind of what these defects do to qubits. And if you look at this plot here, it shows the trade-off between probing these defects with high sensitivity versus probing them with a broad frequency range. Now, traditional methods of probing these defects use resonators or qubits, and those are very sensitive, but also very narrow. Our lab's approach is broadband, meaning that we give up some of that sensitivity, but we gain the ability to see more of the whole picture. So moving on to 2-level system defects. What are they? Well, in amorphous materials, there's in some oxide layers, for example, in superconducting circuits, there are these atoms or groups of atoms that are in one of 2 energy positions. You can think of it like a ball stuck in either one of those 2 valleys, separated by that hill in between. Now, classically, you need some energy to push the ball over the hill. But at the quantum level, these particles can tunnel right through the hill. Now, it's important to note that this tunneling occurs at millikelvin temperatures, cryogenic temperatures colder than outer space, which is a bit of a problem for quantum computing because it means even if we're at the coldest temperatures we can reach, these defects are still there. Now, this equation just shows the energy of this plot with epsilon being the asymmetry energy, and delta naught being the tunnel's. So now that we know a bit of what they are, why do they matter to us? Well, each TLS defect has a dipole moment that couples directly to the microwave electric field within our devices. That can be represented by this interaction Hamiltonian here. Now, these defects tend to concentrate at oxide surfaces, which makes it increasingly painful because that's where the electric field is at its strongest. So this leads to two things. Leads to energy loss, which shortens how long a qubit can hold its state, and it leads to frequency jitter, which shortens how coherent the qubit phase is. Now, this figure here is just a figure of where it's believed that these defects are likely located in Josephson junction qubits. So we know it's hard to see these defects, but we can see their collective response under microwave excitations. So are we able to build a platform sensitive enough to detect different surface compositions through their microwave response? The short answer is yes. That's our BCTDS platform that our lab developed, which stands for Broadband Cryogenic Transmission Dielectric Spectroscopy. Now, we implemented this platform with a WR229 waveguide, which is made of aluminum 6061, and it's shown here on the right. And it has a broadband frequency of about 2.8 to 6 gigahertz. And this plot here are the reflection and transmission measurements that we measured at room temperature. And the simulation and the actual measurements seem to align pretty well, indicating that our waveguide performs the way we expect it to. Now, if we look closer at the waveguide, if you look at the little box in the middle, that's where our samples would go. And then we close the waveguide on itself, so it's each half on top of the other. And then this waveguide with its materials would go into the dilution refrigerator. Then we do a cool down, bring it down to millikelvin temperatures, run a microwave pulse, measure the transient responses we see once the pulse is turned off, and that's what we see here. This is some of our data from actual experiment. And what's important to note here is, well, first, this are some plots of the transient responses that we measured during a cool down of the same sample. So cool down 1 and cool down 2 are the same sample. The only difference is that the only thing that's changed is time. So we didn't change the sample, nothing, and yet the responses are different. The spectral fingerprints are different. And it's clear, panel C makes it clear, showing that these two are not the same. Now, why does this happen? Well, the thermal activation can actually rearrange the spectral signatures of these TLS defects. And although this plot doesn't tell us everything, some of these changes could be due to some spectral diffusion or small changes in the electromagnetic environment. But what it does tell us is that BCTDS is sensitive enough to observe these transient responses. So now that we have BCTDS, is there a way to reconfigure the spectral signatures of TLS defects in situ? Meaning, are we able to change these spectral signatures when the device is already in the dilution refrigerator without us opening it up and making any changes? Well, before I get into that, I want to talk about the work I worked on last summer during my RU here at Dartmouth. I learned how to design, fabricate, and machine these aluminum waveguides, and I made a variation of our original waveguide with this square waveguide. Now the difference here apart from it being a square, is that it has orthogonal ports. And in theory, this would allow us a chance to have more control over the electric field within our device. Depending on which port we drive, we'd be able to point the direction of the electric field. However, when I calculated the cutoff frequency, it ended up being around 1.91 gigahertz, which is well below the target band of our previous waveguide, indicating that this waveguide is not the best for VCTDS. However, and that's clear here on this plot. The simulation measurements of the transmission and reflection are not aligned well with our actual measurements. So that's to say, the main purpose of this experiment and what it taught me was how to design, machine, and simulate and run some basic experiments with these microwave waveguides. So finally, moving on, our optical integration hypothesis. So we believe that when our waveguide is in the dilution refrigerator, a tiny layer of water or ice may form on these surfaces, which leads to the protons to occupy a double well potential, which, as we stated earlier, is an indicator of TLS behavior. Now, what if we had a fiber, an optical fiber, to shine a little bit of heat onto the sample? How would that affect our system? Well, we decided to try and test it. So first things first, we had to create a new waveguide, one that was adaptable to our fiber. So we just did some slight modifications to our original WR229 waveguide with a slot at the top for an adapter and then the fiber connected to that adapter. Top plate you see there is just to allow some pressure onto the adapter so that it stays in place and nothing moves around when you run experiments. Now, the specific fiber we're using is around 450 to 530 nanometers wavelength range, and we calculated the beam radius to be around 4 millimeters. With the sample, with the light being shined onto the sample in the middle would be about a centimeter in length. So in theory, it would work pretty well. And for future experiments, we want to do more wavelength dependent studies, and that would call for a supercontinuum source shown here. So before we could even really run these experiments, we have to make sure that the sample will stay cold when it's in the dilution refrigerator. That seems obvious, but it became kind of a big engineering challenge. So in order to make sure that there was proper thermalization within our system, we designed a new middle ring, which is placed in between the two waveguide halves. And we added these a little thin aluminum shims that kind of push into the sample. And this allows for more contact area for heat to flow better out of our system. And on the right here, we have a design of our fridge mount so that it's able to host more waveguides to run experiments much more efficiently, but also, again, it adds more contact area to the waveguides so that heat can flow out of our system. Now, the waveguides in these middle rings are made of aluminum, but the mount is made of copper. And this is because heat flow is much more important within the fridge. And copper is, the copper we use is high resistivity. And so it allows us to have better heat flow. But for the waveguide, we use aluminum because it's much easier to machine. And since we're making a lot of waveguides, copper is it's too complicated to machine, as it's too soft and it slows down our process. On top of that, we have to make sure that our wiring setup within the fridge is appropriate for whatever experiment we're running. Now, setup one is a setup we had, which has about 23 dB of attenuation, which each attenuator is working towards reducing the forward power and thermalizing the microwave line to its cold stage. Now, for setup two, we added an amplifier and more attenuation so that heat would flow out better than setup one. In setup one, there was still some heat being trapped within our system, but with setup two, the signal, as it moves down the fridge, the thermal noise from these warmer stages is progressively being suppressed. And this is important with our optical illumination experiment, because if we were to shine some light with the fiber, we're introducing a little bit of heat. And with proper attenuation, we'll be able to see what's from the fiber, what's like an actual TLS ensemble behavior, and not just from our faulty setup. Matthias is calling me, should I?
Yeah, put him on. Tell me he's on speaker.
Hello, we're on speaker, Matthias. We're in Jackson conference room. Okay, does this waveguide work as we intended it to? Does it work in the same manner that our original waveguide does, which has been our baseline? The short answer is yes. Yes, the design is different. There are some small changes, but the microwaves we use have big wavelengths, and these small changes that we made are too small to actually affect the behavior of our waveguide. And to test that, we ran some transmission measurements, which are shown here in the plot, with the blue being our original waveguide and the red being our modified waveguide. So yeah, in summary, we have the new waveguide designed, machined, ready to go. It's validated under these room temperature. We've improved our thermalization. We've improved our attenuation and our wiring setup. And now what's left is to run these experiments in the fridge and to record the breakdowns to see if optical illumination actually helps us reconfigure the TLS ensembles. So all in all, what I've learned most about working here is that the physics we want to study influences the engineering decisions we make, what we make, how we make it. And what we make and how we make it, in turn, tells us what physics we can study. All in all, BCTS worked well to develop this platform. Square waveguide helped me develop the skills necessary, and all of this worked together towards our optical integration experiment, which is still in progress and will hopefully continue once I'm gone. Thank you so much for coming.
Student questions, or anybody, to be honest.
Yes.
Yeah, can you tell me more about like how you go about building these waveguides? Like what does the process look like? Maybe like after you've kind of machined them out.
So we're here now.
Sorry?
Like what does it look like to sort of like build these waveguides? Like what are you doing after you've kind of machined it? Is there like some polishing and like what kind of?
Yeah, it's a long process. We have to first design SolidWorks, then code all the tool paths with an add-on HSMWorks. And then when we're machining it, we machine in the machine shop with the Haas Super Mini Mill. And once it's all machined, we have to polish it down. It takes time. We use sandpaper, and then we'll clean it, make sure it's clean before bringing it to the lab. Yes.
Okay, I have a question that may mean that I missed the entire point, in which case don't answer it because I don't want you to explain everything over again, but why is it like necessary, or like what was the point of trying to add heat to the system that you made? Like, how does that like, yeah.
Yeah. So the hypothesis is, well, if these monolayers are forming, then they're also introducing these TLS defects, which affects the performance of these quantum devices. So our main goal is to study these TLS defects, and so if we were to introduce some heat, we would then reconfigure the ensembles, and we'd be able to see if that could lead to improvements or just more about how these defects work, because a lot is still unknown.
Okay, got it.
As someone with really no engineering background, what are these quantum devices used for? Like, what's the real world effect of these?
So we mainly study materials. There are quantum, so the materials we study are what qubits could be made of, or what these quantum devices are constructed of. And the materials themselves have lots of defects that reduce the coherence time of qubits in quantum computing. So quantum computing is still a very new field, but it's what it sounds like. It's a quantum system that could in the future act as a very powerful computer.
I guess first, what's TLS?
TLS stands for two-level system.
Okay, you might have mentioned that. I think it was back when you talked about your fabrication of the square.
Yeah.
And then you have that one, yeah. So, and I think you even mentioned it, right? You've got measurement and simulation.
Mhm.
There's places where you could say, okay, but I mean, it doesn't look very good.
Yeah.
So is that the theory's wrong or what?
No, well,
I mean, it must be, right? Because the measurements are true.
the measurements are mainly based off our original waveguide, which is made for BCTDS, made for this broadband frequency measurement. This is not made for that. So this was just it was kind of a given, but this is just to solidify the fact that this waveguide would not work well with our platform. This waveguide had the alternative motivation of introducing the orthogonal quartz to be able to have better control over the electric field.
So just so you'd have to change the theory if you wanted to use this particular.
Yes.
Okay.
But isn't you're asking about the agreement with the experiment and the stages themselves, right?
Say again. I'm sorry.
Are you talking about
Wait, who are you?
the curves? Yeah.
Yeah, I mean, I'm like, maybe in your field that's good agreement. I don't know, but I'm just looking at it from the.
So what? How could you make it better?
Yeah, I mean, it could be due to it could be to how it was machined. You know, this was me still learning how to, there's a lot of trial and error with this square waveguide. It could also be just how these measurements were taken, or the orthogonal quartz weren't properly orthogonal in place.
Wait, but is the agreement worse than this one than the normal waveguide?
This one is worse, yeah, 100%. This agreement is much worse than the original waveguide. But, well, the original waveguide being this one.
Yeah. How would you quantify that?
I mean, you can eyeball it. It doesn't seem to overlap too well with the dashed lines or the simulation. But open to interpretation. If you think it looks okay, then I'll take the win. Yes.
Just kind of following up on this,
Mhm.
what's the importance of the reflection measurements in this case? Like you've got S2 long range transmission is what you use for DCTDS.
Mhm.
What do you use reflection for then?
Well, it's important to measure reflection because when we're running experiments, we will be getting some reflected data, and that is not, is affecting what we actually want to look at. So it's important to have a good idea of what data is being, or what waves are being reflected within our device.
Great, okay, let's thank Sophia. Thank you. Thanks for coming, everybody.